And we're back on another episode of Think on That. This is the Everything and Anything podcast. I'm Matt Goody.
Got your boy Alex.
And we've been gone for a little while, so I'll apologize now. I had a funeral I had to go to 1 week, and then we were just chatting with our guest here. The lost episode of last week.
Should we tell the story? Yeah, why
We'll tell the story. Let's introduce our guest first.
Yeah.
Our guest is a theoretical physicist who studied at Cambridge and is currently doing his PhD at...
University of Toronto.
University of Toronto. Ooh, this guy's like Ivy League all the way. Anyways, Mike Imseis. We went to elementary school together.
We did. Way back when. Way back
A
when.
million years ago.
Oh, wow.
Yeah, man. Welcome to the show.
Thank you. It's great to be with you guys.
I'd like to reiterate what you do. You are a theoretical physicist.
Theoretical physicist. That's
We've been
right.
teeing you up. We've been excited for you to come on the show for a while.
I've been excited to be here. Yeah.
So we're going to dive right into it. But first, we're going to tell the story about the lost episode.
Yeah.
Yeah, we have to.
Yeah.
So yeah, we're at a cottage, right? We had this all planned out. We're gonna bring the camera. We're gonna bring some mics. We're gonna kayak out onto an island. Beautiful spot, water in the background, the whole 9 yards.
On a bright, sunshiny day. It was the perfect morning.
Beautiful day. We got there right on time. Everything was going well, and I had a weird hunch. I got up about an hour in, went to the camera, and it was not recording. An hour into a great conversation that we will have again, and we'll have to release.
That's what we said to each other.
No,
we
it's
tried
fine.
to make the glass half full. We'll come back.
Yeah, exactly.
We're gonna come back stronger.
Yeah.
Are you guys going to go to the same spot? Like,
No.
in the
There's
cottage?
no-
Or
It was so far away.
Yeah, it was like 2 hours
Oh,
away.
okay.
That's
And
fine.
but it was on a quiet, secluded lake on this tiny little island in the middle of this lake.
Oh.
And like this island I'm talking is like no bigger than this condo. Like it is.
Really?
Yeah, small.
Where's the cottage again?
Boy Lake,
Perry Sound, yeah.
Perry
Oh,
Sound,
okay,
which
okay,
is Boy
okay.
Lake. Yeah,
Yeah,
Okay.
beautiful, pristine.
Oh, wow.
2 hours
Yeah, man.
outside of Toronto.
It was a heartbreaker.
Yeah.
Well, I think I could speak for all the fans that you have when I say, we want that episode. We want that episode.
It was good.
Yeah.
It'll
But
come.
we want this episode, so let's dive right in.
Yeah, we've
Let's
been
do
itching
it.
for this one.
Okay, so before the show, I kind of asked you really quickly what your like specialty was in theoretical physics.
Yeah.
And you said,
Well, yeah. So, of course, theoretical physics is very broad. So, what
Right.
I'm interested in is something called quantum gravity, string theory, black hole physics, that sort of thing, origin of the universe, that sort of thing. So, it's quite an interesting subject and quite a heavy subject for people when they first get introduced to it. But hopefully, I can sort of answer some questions that you might have, and we could talk a little bit about specifically what I do.
right.
How long have you been studying those?
So I will tell you how I got interested in
Okay.
physics, because when I was in high school, I graduated high school in 2015 from St. Max,
Right.
and I had not, at that point, upon graduating, upon throwing that cap in the air, I had not taken a single physics class, math class. The only science class I did was biology in high school. And so people, when I tell people that, they're like, how did you ever get into university and stuff?
Yeah.
So I don't know if you remember, for the graduating classes, I think every year they had this thing called S-Trip, right?
Right.
So I went on S-Trip. We went to Punta Cana just for a graduation sort of vacation over March break, I think it was. And it was a great time, had a lot of fun. And on the plane ride home, and sorry, I had applied to university before this for like sport business or something, got into a few, got rejected from a few. And then on the plane ride home, I decided there's a lot of hype about this film called Interstellar. And so on the plane,
Oh yeah.
Yeah.
right, it's an
One of the
extraordinary
best.
movie.
One of the best.
Some might say life-changing movie.
Absolutely.
Right.
So when I watched the movie, there is a scene in the movie. I haven't seen it in a long time, so I guess it was they're on like a planet or something, like a water planet.
Yeah.
Right.
Yeah.
And they were on the planet. There was one guy in a space station orbiting, and it was something like an hour for the people on the planet was equivalent to 7 years for the guy
Yeah.
Yeah.
on the space station.
Yeah.
And I thought, I was watching that, and I'm like, really?
Yeah.
That seems like science fiction. How could time run differently for different people, depending
Yeah.
on where they are?
Yeah.
So I went home after watching that movie and started to do a little research online. And wow, this thing called relativity, Einstein, and sort of what his ideas, and that led me into a little bit of quantum physics. And wow, this is really interesting.
Wow.
And so I decided to reject all of my university offers, and I had to do summer school for 11th grade physics, and I went back to do a victory lab to do 12th grade physics, calculus. I did calculus in night school, advanced functions, that sort of thing, and reapplied for physics and astronomy, and ended up going to University of Waterloo for my undergrad. So that was ever since like 2015-ish,
Right.
to answer your question.
Okay.
So it's been about 8 years
Wow.
that I've been interested in science
Your
and
brain is extraordinary. Because
Yeah.
I have hobbies that I picked up and interests I picked up after high school, because I've had a very, very like diverse career background.
Yeah.
But man, for you to just be like, oh, relativity.
Most people.
And then
most
you're
people,
like getting a
yeah.
PhD. You have
Yeah.
a fantastic brain.
Well, look, I'll tell you sort of why I got so captivated by it, and really, I think, you know, I can't remember who said this, but somebody said, I think it was a famous physicist called Richard Feynman, and he published a lot of books, right? Mm-hmm. And somebody said to him, for every equation in your book, you're going to reduce the number of sold copies by half. Because people don't like equations.
Right,
people don't
right.
like math generally. They just want the ideas. But for me, in looking at videos on YouTube and watching professors explain relativity, quantum physics, when they would write the math on the board, of which I had no idea what they were writing,
Right.
there was something in me, I guess kind of like when people look at ancient Egypt and look at hieroglyphics, they're like, what does this mean?
Right.
That's what I had in my mind when I
Curiosity.
saw this.
Yeah.
It was just a curiosity. What does this mean? This is so fascinating. The idea of gravity as something called curved space-time, and quantum mechanics, and something called quantum field theory, and it was the math that actually drove me to want to understand that better.
Mm-hmm.
So yeah.
Wow.
That is, yeah. Wow.
Safe to say he's not a flat earther. I highly doubt it.
I'll debunk flat Earth if you want, but you know, we can sort of talk about that later.
Okay, so one of the things that I'm particularly interested in, well, both of us actually, we spend a lot of time talking about it, not just on the show, but personally too, is like, you said, like the origin of the universe and like ancient beings, and like, we often talk about ancient civilizations on Earth, and like our perspective is sort of like, oh, you know, sentient, intelligent beings have probably lived on this Earth for like hundreds of millions of years, you know? So what was the universe like then? And like, were there like people who were traversing it and all that stuff?
Yeah.
We've had those kind of questions, but I mean, before you can even get to that, we went to you because we want to understand like the fabric of the universe.
So do
That's
I.
a good starting place, right?
Yeah, for sure. That's probably the bare starting place, because these questions are addressing the fundamental structure of what the universe is made out of. That's really what I study. I'm in the high energy theory group at University of Toronto.
Okay.
And so we have people in our group trying to understand particle physics. We have people in our group trying to understand what is space-time made out of, which is what I do. And so we're really talking about the fundamental nature of what this place is.
Right.
Right.
So what is this place?
Well, this place is a very vast place, full of stars, galaxies, planets, interstellar gas, interstellar dust. Of course, we only know, at least at this point in history, as I sit here talking to you guys, we only know roughly 5% of what the universe is made out of. So you look at these photos, these beautiful photos by Hubble Space Telescope or
And the
by
Webb,
the James Webb Telescope.
Right.
And you see all of these galaxies. Every dot in that picture, except for the ones with spikes, those are stars in our own galaxy. But every dot in that picture is a galaxy, each containing 100 billion to 200 billion stars themselves.
Right.
And so you see a vast array, all of that stuff, all the galaxies, all the planets, all the stars, all the dust that's out there. 5% of the universe.
It's a lot to grasp for sure. I'm sure also for you, but even to your average person, when you explain that to them, and then they say that the universe is also expanding.
It's not just expanding; it's accelerating as it's expanding,
So-
as far as we could tell.
What does that mean? Like, where is it expanding to, and How do we know it's accelerating?
So I'll do the second question first. Okay. How do we know it's accelerating?
Yeah.
So if you've ever have been sitting on a bench or something and an ambulance drives by,
right.
What you'll hear the ambulance and its high pitch alarm or whatever you call that.
The siren.
The siren, yeah.
Right.
And as it's coming toward you, you'll hear it at a high pitch because the sound waves are it's coming toward you, so the sound waves are being sort of crunched up as they come to you.
Yeah.
And as it passes you, the pitch of the siren goes down, so you hear it as lower.
Okay.
That's true.
Right? Because the sound waves are being stretched now because it's going past you. It's going...
Right.
Right?
Yeah. Right.
So these are sound waves that do this. This is something called the Doppler effect.
Right.
And so light can be thought of as a wave in certain regimes. And so basically what we do is we look out into the cosmos and we see galaxies and stars within the galaxies, and these galaxies are radiating at particular frequencies of light. Okay, and we know what these frequencies are. That's how we know what stars are made out of, because we know if the sun, for example, is radiating light, and some of the sun's atmosphere is absorbing that light, and it absorbs the light at very specific frequencies depending on what the sun is made out of. Okay.
Holy shit! So we
right.
figured that out.
So we figured this out. Yes, and so when we look at galaxies that are moving away, galaxies do this as well, depending on what the stars in the galaxies are made out of, depending on their composition.
Does their proximity to other galaxies affect that too?
Sorry?
Does their proximity to other galaxies affect that too?
On cosmological scales, no, not particularly. No. What we're really talking about is observing the light from the galaxies.
Okay.
So the light of an individual galaxy doesn't depend on the other galaxies surrounding it.
Right.
Okay.
Anyway, so these galaxies are radiating at particular frequencies. And we know what these frequencies are because we study these frequencies in our labs, right? We know the specific wavelengths that these frequencies of light are at. When we look at the galaxies that are receding from us, we see that they are a little bit more red. The galaxies appear a little bit more red. And that's because as the sound waves are getting longer and longer as the ambulance goes away from you, the light waves coming from the galaxies are getting stretched, and longer wavelengths correspond to more red light. And so when we look at the light and we see, it's slightly red shifted, we call it, we know that the universe is expanding. And when we calculate, we can figure out what the rate is at how fast these galaxies are moving. And it turns out that if a galaxy is twice the distance away from us, then it's going to be moving at twice the velocity as compared to a galaxy that's, let's say, like if a galaxy was 1 light year away from us, let's say,
right,
it'd be moving at some velocity. If another galaxy was 2 light years away, it'd be moving at twice the velocity of the first one, right? It's a linear relation. Anyway, so we could figure out how fast they're moving away from us, and it turns out that as far as we could tell, they're too far away from us than what our math says. So we say, and there's experimental data on this, so we conclude that it must be getting faster and faster, the universe. And that's what, and this is related to something called dark energy. Dark energy makes up 70% of our universe, and we have no idea what it is.
Is this what they refer to as dark matter?
Dark matter?
Dark matter is something else. Dark matter is
dark energy and
fuck me.
dark matter.
When you think you know, eh?
So as I said, 5% of our universe is
shit.
known, is the matter that we know of. 25% roughly is dark matter.
Okay.
Dark matter, we think, are contained mostly in halos around galaxies. Dark matter doesn't, as far as we could tell, interact with any known interaction except for gravity. We know that it interacts gravitationally because it affects how galaxies rotate, for example.
Right.
That's 25%, and then 70% is the dark energy that we think is causing the universe to accelerate in its expansion, and we have no idea what these things are.
What if
We have
these two
absolutely no
things
idea.
are like two separate like universes within our own universe? You know what I mean? Like a layered co-multiverse existence. But like everything that's dark matter, we can't perceive it or understand.
We can
it.
get into we can certainly get into that and sort of
Just a question.
yeah.
You know, just Gavin. Just Gavin. I'm kidding. Please continue. I'm fascinated.
Yeah. Anyway, so that's how we know the universe is accelerating and that it's expanding. And interestingly, when Einstein first wrote down his equations of gravity, his equations of general relativity, you could solve them for an expanding universe. Einstein didn't really like the idea of an expanding universe. He liked the idea of a stationary universe.
Right.
But the problem was when he first wrote down his equations in 1915, what they predicted was a universe contracting in and on itself. And that kind of makes sense because gravity
It's
pulls
pulling.
things together. So
right.
gravity wants to pull the universe in, right? He didn't like that idea. He thought the universe had to be static. So what he ended up doing was modifying his equation a little bit to introduce an extra term in his equation called the cosmological constant.
Einstein is tarnished.
And what this... hold on.
Settle down over there, buddy. You're blowing this guy's mind.
So what this term in his equations did, what it provided was on big cosmological scales, it produced a slight repulsive force to counteract the attractive force of gravity to make a static universe.
Right.
Now, of course, many, many years later, we discover that the universe is not static. Actually, in 1929, it was Edwin Hubble, former lawyer turned astronomer. That's great.
Nice.
Edwin Hubble looked out and said, "Whoa, the universe isn't static. It's actually expanding at this particular rate, Hubble's law." Einstein was wrong.
Holy shit.
Until in 1999, I think, we discovered that the universe is, as I mentioned, accelerating it in its expansion, which means that Einstein was right because that repulsive force is so repulsive that it's sort of, you could think of pushing out on the universe, causing it to go faster and faster.
Right.
And so this number, which is a very important number called the cosmological constant, it's just a number,
Right.
is slightly positive. And that's what's causing the universe to, we think, accelerate.
Yeah.
The problem is when we try to calculate what this number is through our methods of quantum field theory, for our methods of how we calculate things, we predict this number to be very, very big. And if it was this big, then it would wipe out everybody. And stars couldn't form, and planets couldn't form, and galaxies couldn't form. So the problem is, why is this number so small? It's slightly positive, but why is it so small? And nobody knows. This is the problem of dark energy. This is, how do we get this number to be very, very small? Right. Nobody knows how to do it. Yes.
Mystery to be solved.
Oh my. I've had a brain kaboom moment.
So, before Einstein, you mentioned that, because I remember reading a while back that ancient Greeks used to think that the universe, that Earth was the center of the universe, and that everything was pulling towards Earth, which I don't know if that would mean that the universe would be shrinking and not so was that the consensus before Einstein? And then Einstein said, no, that's all wrong. It's static. Like, what was the consensus before Einstein?
So you're talking about the geocentric model of the universe.
That's exactly what I was thinking.
Which puts Earth at the center, right? And so this was how people thought about our place in the universe all the way up until a guy called Nicholas Copernicus.
Okay.
In
Copernicus, I've heard of him.
1500s, I want to say.
Okay.
And he proposed that we weren't the center of the universe, that the sun was the center of the
Solar
universe,
system.
right?
Or the universe.
That the sun was?
Well, because at that time we didn't
Yeah.
know about other solar systems. And
Right.
We just
Right.
looked up and we saw stars. We didn't know that these were other solar systems.
Right.
So he proposes this. Of course, the church doesn't like it because God created the universe and we have to be the center.
Right.
So they did not so great things to him. Same thing with Galileo. Galileo, when he discovered that there's moons orbiting Jupiter, he said, "Oh, look, there's moons orbiting Jupiter." But that also meant that there were things that were orbiting things that weren't us. There's Jupiter.
Celestial bodies.
Celestial bodies, exactly. So
Interesting.
the church didn't like that, and so they did some not so great things to Galileo.
Right.
Wow.
It only over time, yes, it was generally then we looked out into the cosmos, we discovered other planets, other things, and we saw other star systems and planets orbiting those, and so yes, gradually we came to accept that the sun was the center of the solar system and that we were just on the outskirts of a galaxy and with 100 billion stars, and there's 100 billion galaxies roughly in the universe.
I have a bit of a loaded question for you.
Sure.
And it's a personal question, so
All
you
right.
don't feel obliged to answer if you don't want to.
Okay, well, let's see.
As a theoretical physicist,
Yes.
you have obviously been exposed to concepts and like proven, I don't know, what do you call them? Conclusions
Yeah.
That
Proven
have-
theories, proven.
that
yeah.
shatter like your like universal outlook
Yeah.
as raised by a Catholic kid, because that's
Yeah.
what we were. We went to
Yeah.
Catholic school, we were raised by Catholic people.
Yeah.
What is your like relationship with like God and religion now as a theoretical physicist?
Yeah. So I would say, yeah. So I grew up Catholic, right? We went to Catholic school, high school, elementary school together, and I believed in God. I prayed most nights during high school, and then so then when I discovered science, when I discovered physics, and started to learn about some of these things, my faith kind of diminished significantly, right? And so I became what people would call an atheist, let's say.
Okay.
And that it was like that. I would say up until a couple of years ago. Now, I'll tell you what kind of changed my mind. And I was listening to another podcast, the Lex Friedman podcast. You probably
Right.
have heard of him.
Right.
And there was another. The podcast host was a Stanford neuroscientist called Andrew Huberman,
Yeah.
and
He's been on Joe Rogan before.
Yeah.
he's been on Joe
Yeah,
Rogan
he's
a couple
good.
of times. Yeah, and he was describing an experiment, a neuroscience experiment that these people. I think one professor was in Stanford, another one was at NYU, collaborating.
Right.
And the experiment that he was describing went as follows. There was some animal, I think it was a monkey or something. I don't think he specified what animal it was. And there was a screen in front of the animal. And the animal was trained to like hit a button or something every time there's dots on the screen moved up on the screen. Okay? Every time they moved up, the animal signaled, yes, I see them moving up. And gradually what the researchers would do were they would take one dot and move it around, not up, and they would, maybe take 50% of the dots and then scatter them around, not moving up. And slowly they were all just all over the place, not moving up, right? The point is they trained them very well to notice when these dots were moving up on the screen. Now, neuroscience is very cool. My girlfriend does neuroscience. What they can do is they can go into the brain of this animal and they can silence and basically control the neurons that tell the animal that the dots are going up on the screen.
Right.
So what they do is they go in and they silence the neurons, meaning that when the dots go up on the screen, the neurons don't fire, and therefore the animal doesn't hit the button.
Right.
So it doesn't see. But then what they did was they made the dots on the screen, all of them, move down. At the same time they did that, they made the neuron fire in the animal's brain, telling the animal that the dots are moving up, and the animal hit the button. So in other words, in reality, the dots are moving down on the screen,
Right.
but because the neurons, and this might be an obvious point, but because the neurons are telling the animal the dots are moving up, The animal perceives them as moving up. So what this means is our constructed reality is solely based on our neurons firing. So there could be, and this was my thinking back then when I was watching it,
Right.
I was thinking there could be, the underlying structure of reality could be such that we don't perceive it because our neurons are not firing.
Wow, well, it goes back to that whole
Right.
dark matter stuff.
And in fact, we know this is the case because, so just a quick side comment, the way stars work are you have a bunch of hydrogen in the core and it's nuclear fusion. So the hydrogen is very hot, it fuses together. When this happens, it releases light and it releases these particles called neutrinos. Neutrinos don't interact very strongly with stuff. In fact, the light, when that happens in the core of the sun, the light that's released from that interaction takes, I think, on the order of 1 million years to get from the center of the sun to the surface of the sun.
Holy.
Right.
Because it's doing a random walk through
Right.
the
Oh, yeah,
interior.
okay.
Right.
Right? Neutrinos, on the other hand, these little particles, don't interact very much with anything, so they just go straight through.
Right.
So what that means is there are roughly on the order of 6 billion neutrinos passing through every square inch of your body every second of the day, because these things just flow right through Earth as if it wasn't there. So these things, in other words, these things exist, and we know they exist because we can measure them with our apparatuses, but they don't register any neurons firing in our brains. So to answer the question about God and about faith, I kind of changed my tune a little bit and I'm not so atheistic anymore, and I recognize that, there could be something about fundamental reality that isn't in the material world,
Right.
right?
Interesting.
Now, whether or not that makes Islam or Christianity or Hinduism or Buddhism correct,
Right.
I don't know.
Yeah.
Right.
All I'm saying is I believe in it a little bit more.
That is a profound way
Yeah.
to find faith. That is crazy.
A scientific way,
That
you know?
is-
Yeah.
See, that's what I mean. I know quite a few scientists, just casually, and I've asked this question before. Maybe that's why I'm so brazen with it. But they've said no, I just don't. And I'm like, that's the answer that you almost expect from a scientist, to kind of be like, look how wrong your theories are. But this is the kind of God that I talk about. This thing that is so vast and powerful, it's beyond human comprehension. And I think people have a hard time with that idea.
I think
something
so.
Yeah,
being beyond their comprehension.
I think it's
Yeah.
human nature. People want to understand things,
Yeah.
and then when something's so vast like that, like you said, that's uncomprehendable, then I think you'll veer away from it, right? And then that might lead people to believing in more in science, which there's nothing wrong with, obviously.
It's part of the
But
story.
and then
I
that's
think just part of it, though.
that's
I think, I think people often, some people might say science and religion cannot coexist. This is obviously not true because
Yeah.
Newton was a believer, and
Right.
everybody, even during the Enlightenment, they believed in God. Newton believed in alchemy, the idea that you could turn ordinary objects into gold.
right.
I think people confuse religion and science in the way that, when you ask a scientist, do you believe in God, they'll immediately point to empirical evidence and say, well, there's no evidence for it, so therefore I don't.
Right.
Fine, but religion is not science, so religion is faith-based.
Right.
The same way you ask a religious person, do you believe in God? They say, of course. Look at all of this evidence. Well, as soon as you bring in evidence, then that's not faith anymore, because faith is, by definition, believing in something without evidence.
Exactly.
Now, so you can make somebody could make an argument, maybe as just I just did for perhaps believing in something that's deeper than our material universe.
Right.
But at the end of the day, I have to recognize that I could be wrong at the end of the day.
Well, that's
and it
just
could
it.
not be the case. But it's a faith in it. It's not science. Right? And even when... So I've been listening a lot to this religious scholar called Reza Aslan. And he makes an interesting point that I still have to think about a little bit more. He makes the argument that that people shouldn't... The notion of believing in Christianity or believing in Islam or believing in Hinduism or any other religion is actually false, because you don't... He makes the argument you don't believe in these things. These things are a medium to get you to the thing to believe in.
Right.
Right?
Yeah.
Right.
For real.
Yeah.
In other words,
describe it.
I think Buddha made this analogy. Like you have, you don't, to get to the water that's 6 feet underneath the ground, you don't build, 6 1-foot wells. You build 1 6-foot well to get to the wall.
Yeah.
But at the end of the day, you want to get to the water. You don't believe in the well. You want to get to the water, right?
Right.
Yeah.
So
The well is the tool to get you there.
Exactly, it's just a tool.
And that's what something like the church is. Yeah.
Exactly. So that's my take on it.
That's a very good perspective.
Yeah.
So have you changed your relationship then with the church as like an institution?
Well, the church. Look, I not really. I mean, I don't really believe much of the Old. See, that's the other thing. When the thing like the Bible was written, so what I think people do is they're taking their notion of what they think truth is,
Right.
and they're mapping it onto this book that was written 2,000 years ago.
Yeah.
The people that wrote the book 2,000 years ago had a different notion of what truth was, because the
Right.
scientific revolution didn't happen yet.
Absolutely.
Right.
When the scientific revolution happened, our definition of what truth was changed. And so I do think Jesus was a real person. I think he did walk this earth. I think Muhammad was a real person.
So, yeah,
I think Buddha was a real person.
Right.
These people, I think all of them were here just to point to something, I think that's hidden, that's deeper about reality. Whether or not they're right or wrong, I think it's worth exploring these ideas.
Yeah.
Absolutely.
Yeah.
That is a very good explanation.
When people when people do the religion versus science, I think the topic that comes up probably the most is like the Big Bang Theory, the start of it all, right?
Yeah.
Which at the end of the day is still a theory, right? The Big Bang Theory,
Well,
but is it proven?
Well, we have a lot of evidence for it. Interestingly, the Big Bang Theory was first proposed by a priest.
Right.
Priest in I can't remember where it was. I want to say it's the Vatican, but I don't think it's the Vatican. His name was Georges Lemaitre.
Wow.
And so there's a lot of evidence for the Big Bang. In fact, there is an afterglow of the Big Bang that permeates the entire universe.
Right.
It's
Yeah.
called the cosmic microwave background.
Right.
And this is directly testable. We've gone out, we've seen it. This is predicted by the Big Bang Theory, because the universe at that time was very hot, and there's a lot of radiation. That radiation was left over. We have a lot of great evidence. For example, Big Bang nucleosynthesis, which is the idea that when matter first came into existence, similar to like how stars, there's nuclear fusion. Well, that was happening back then too, during the Big Bang. And so we can make predictions about how much helium there is in the universe and how much hydrogen there is in the universe.
Right.
Based on the Big Bang model, we go out and we test these abundances. They're very much in line with our predictions.
Wow.
So the Big Bang is very well tested.
Right.
What I would say is, we know something happened back then, 13.6 billion years ago. We're pretty confident in running the clock back all the way to about 10 to the minus 33 seconds, which is 0.33 zeros and then 1
Right.
seconds after. But we don't know what happened at t equals 0 or time equals 0. We don't know how it came into existence.
Right.
This is the idea of quantum gravity. The only way that we're going to be able to say what was before the Big Bang or how the Big Bang came into existence, how the universe came into existence, is to have a proper understanding of this idea called quantum gravity, which is what I work on.
Oh,
Very interesting.
man. This is like the fabric of God himself you're dealing with here.
Yeah, yeah.
That's pretty cool stuff.
Do you think
Yeah.
that God and the Big Bang Theory, I mean, this would be opinion based, obviously, but, that it would go hand in hand? Like, it could go hand in hand? I mean,
Well, so before the idea of the Big Bang Theory,
right.
the idea that the universe had a starting point
Right.
was not really mainstream in science.
Right.
It was the religious people and the people that believed that in a creator that created the universe that said the universe had to have a beginning because God created the universe, so it had to have a beginning.
Right.
And it turned out that we think that is correct. So they do, in some sense, go hand in hand. Whether or not a being literally created the universe, I don't know. I just don't know.
Yeah, then it goes back to a common question of, well, who created the creator, right?
Exactly. And I think some religious people might say, well, he's an infinite being, or it is an infinite being
Right.
outside of our space and time, therefore it doesn't need a creator, which,
Right.
if they want to believe that, that's fine. But I personally, I just don't know. Yeah.
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 It's uncomprehendable.
Uncomfortable.
It really is.
It
yeah.
really is.
Yeah.
Like, it's...
Which is exactly what I've been saying. That's exactly where it should be. I think it's supposed to be perfectly uncomfortable to just not know because it's so vast. I mean, what is a God particle? I'm sorry, that just popped into my head. What is a God particle?
Good question.
It's a great question. All right, the God particle. I'm trying to think of how to start this.
Wow, this is exciting.
So. In the early 20th century, people were starting to think about something called quantum physics. Okay, quantum physics deals with particles that make up atoms, and atoms make up objects, molecules, and molecules make up objects. And so people were thinking about quantum mechanics. People like Erwin Schrödinger wrote down his equation,
Right.
Schrödinger's equation for a quantum particle. But then Einstein had his theory of relativity, and people asked, well, can we combine these two? Can we combine special relativity and quantum mechanics, as Schrödinger saw? The answer was no, you can't do that. The reason you can't do that is because when you try to combine these two things, what you'll end up getting is that something called particle number isn't conserved. What that means is you could have, when you combine quantum mechanics with special relativity, you can have particles zipping along and then pop out of existence and then pop back into existence. So the number of particles in your process isn't a conserved quantity when you combine these two things. And this was something that Schrödinger's equation could not capture.
Right.
So we needed, if we wanted to unify quantum mechanics with special relativity, we needed something else, and that something else is something called quantum field theory. Quantum field theory is the idea that there is really no such thing as particles. What they are fundamentally are fields that permeate the entire universe. What is a field? A field is an object that takes a value at every point in space and time. For example, the temperature in this room. The temperature in this room, if you go to one corner of the room, might be one value. Another corner might be a different value. Right? So,
like ever standing constants everywhere you go.
not constants, and well, I mean, depends on what you're talking about. But quantum fields are not constant; they evolve in time. Okay. So quantum fields. So, for example, there's an electron, right? There's an electron field permeating throughout the entire universe, And what we call an electron is a little blip in the field, a little excitation in the field. Light is an electromagnetic field, and little particles of light called photons are little blips in the field.
Right.
And so on for other elementary particles like quarks, like the God particle, Higgs boson it's called. So we took this theory of quantum field theory, and we tried to construct theories about relativistic theories, taking into account Einstein's special theory of relativity, relativistic theories of the particles, the elementary particles that we saw, like an electron, like a proton, neutron, that sort of thing. And it's very successful. It's very successful. So we have something called quantum electrodynamics, which deals with which is a quantum version of light, right, and how light interacts with matter. We have something called quantum chromodynamics, which is the quantum version of what is referred to as the strong interaction. The strong interaction holds protons and neutrons in atoms together. Because if you remember from high school, like charges repel and opposite charges attract. I don't know if you remember this. So if you have two protons that sit next to each other inside an atom, inside the nucleus of an atom, they want to repel, but the only way they can't repel is if there's some force holding it together.
Right.
And that's the strong nuclear force we call it.
Wow, okay, cool.
Okay.
There's something called the weak nuclear force, which governs decay of particles, like the decay of the neutron. That's governed by the weak interaction, weak nuclear force. All of this, strong, electromagnetic, weak, are governed by something called quantum field theory. That's the language.
Okay.
So we constructed what we call the standard model of particle physics. The standard model of particle physics, and in particular quantum electrodynamics, is the most precise theory that humans have ever come up with in history. We can make a prediction. The electron is spinning. You can think of it as a little spinning particle. The fact that it's spinning tells you that it responds in a particular way to magnetic fields. And we can calculate the strength at which sort of it responds to magnetic fields using this thing called quantum electrodynamics. And it's a number. It's called the gyromagnetic ratio. It's 2 point and then a bunch of decimal places. The theory, and I just did this in my quantum field theory course, we can make this prediction, this number that we could just math, just on a piece of paper. We make this prediction, it comes out to 13 decimal places. We can make this prediction. We go out and we test it. Every decimal place to 13 decimal places is exactly the calculation that we performed.
Wow.
So in other words,
13
decimal places. This is the most accurate theory ever existence, ever to be created. Anyway, we have the standard model of particle physics around numerous predictions, numerous Nobel Prizes, numerous experimental validations. It's very well tested. There are some slight problems that we can get into. Very well tested. There's one thing that was wrong with it, and that was there was no way to generate a mass for the particles like the electron or like these particles called quarks. Quarks make up protons and neutrons. There's no way to generate a mass for these things. So the theory was said these things are massless. They don't have any mass. Well, that's obviously not the case because we're massive and we're made of these things. So they have to have mass. Where does the mass come from? So this guy called Peter Higgs, who was at the University of Edinburgh, back in the 60s...
I can feel it. This is about to fuck me up.
Back in the 60s says, let me introduce another field called the Higgs field, which is slightly different than the other electron field. And electron field has spin, photon field, light has spin. These things have different spin, but they have spin nonetheless. This Higgs field doesn't have spin. It's what we call a scalar field. And he said, let me make this field interact with the particles in such a way as to generate a mass for these particles. Okay, you could do this. And in fact, this goes into something called... So it turns out that the weak nuclear force has to be sort of unified with the electromagnetic force at the high energies. And at low energies, this unification breaks into electromagnetic force. This is controlled by Higgs's particle, the Higgs boson, and this breaking of the symmetry, yeah. So these are things that we haven't discussed yet. But the standard model, the quantum field theory, is based on symmetries, and these symmetries can break because of this Higgs particle, this Higgs field. The point is, he did this in the 60s, and he was able to generate a mass. But people didn't see this in any experiment, and not all the way up until 2012, which is when we turned on the Large Hadron Collider in Switzerland. When we turned this on, when we fired protons and smashed protons together, we finally slapped the Higgs field so hard that it produced a particle called the Higgs boson, or the God particle. So the God particle, to answer, this is a long answer.
Wait, humans made a particle?
Well, humans made an experimental apparatus, the Large Hadron Collider, to figure out that the particle was there. So in other words, they took protons, they smashed protons together, and it created so much energy that it created one of these particles.
That it created that particle. Oh, okay.
Called the Higgs boson.
Okay.
And why do they call it the God particle? Well, because it gives the particles mass. That's the point. And that's what it is. Yeah.
Makes things real.
Yeah.
Brought it into fruition.
Yes, wow. Yes. And so he got the Nobel Prize.
Wow.
He did this in the 60s. He had to wait, 50 plus years until finally they found it. And
was he alive when he got it? Or
yeah, he's still alive.
Oh,
At the University of Edinburgh in Scotland.
Cool.
Wow, good for him. He made it to see
He made
it.
it to the big time.
Yeah.
With the God particle.
Yeah.
Jeez.
Wow.
This stuff is crazy.
It's crazy. Science. It's so mind-blowing. To me, the reason why I was interested in theoretical physics is that I think it's mind-blowing that, like I mentioned before, this number that you could predict, the 13 decimal places. Look, people in high school say, they learn math and say, when am I going to use this math? When am I going to use this math? I'm learning about these parabolas and these y equals mx plus b, the line, and when am I going to ever use this? You can think that, okay, if you're not a physicist or an engineer or something, fine.
Yeah.
When are you going to use it?
Yeah.
But the fact that human beings are able to take these silly little symbols that you can write on a piece of paper. I can write you the entire standard model of particle physics in 1 inch on a piece of paper.
Wow.
And this thing describes very accurately the entire universe that we see modulo gravity. It doesn't have gravity in it. So, and that's the whole idea of quantum gravity. But anyway, that's the reason why I enjoy theoretical physics, is because I can write down these symbols and predict things about the real universe. That's really cool to me.
And that's kind of like the only way that you can really explore the universe, right?
Yeah. I mean, it's one of the ways. Again, another way, you have very deeply religious people who can come up with religious truths and truths about sort of maybe morality and stuff. That's another way.
Right.
But if you want to talk about the fundamental structure, what is this place made out of?
Yeah.
Theoretical physics, in particular high energy theoretical physics,
Right.
does this.
Yeah.
Is this the exact same stuff that Sheldon Cooper does?
Sheldon Cooper from the Big Bang Theory studied string theory, I think.
String theory, yeah.
String theory is something else, if you want to get into it.
I remember Penny on the show asking him, so what's new in string theory? And he looks at her and he goes, nothing.
Yeah, I mean, I can't remember exactly. I can't remember exactly when the episode.
Yeah,
I remember
yeah.
that. But look, string theory has been around for 50 plus years.
Right.
A lot of developments, a lot of very big developments have been made from string theory, but it has yet to produce a testable prediction. It's still a mathematical framework that we don't know if it's actually corresponds to our own universe or not.
Can you explain how like the funding system works in terms of like the universities and you know what I mean?
Well, the way I don't know too much about it, but I think the way it works is you have professors who get hired by the universities to teach and do research.
Right.
They have a salary from the university.
Right.
And then depending on what area, if you're more of an experimentalist and you need equipment to buy and stuff, or
Right.
I'm a theorist, you just need a pen and paper. These researchers apply for grants, government grants mostly. Sometimes grants from, sometimes a company will give a scientist a grant to do some research in biology or something.
Right.
But for physics, it's mostly government funded, and so you apply for these grants. Some people get the grants, some people don't get the grants, and then you get to do with it basically whatever you want with that money.
Right.
And obviously, you want to do your research with that money,
Right.
right? And take on graduate students with that money and stuff.
Right.
So right now, it's all pretty much government funded,
Right.
which, in my view, I think needs to change. I mean, it's very weird to me that science in some ways is so underfunded.
Right.
Especially graduate students wanting to become scientists basically don't make anything. They make a little bit from teaching and research,
Right.
but certainly not enough to live in Toronto.
Mm-hmm.
And yeah, it's weird to me that you have biologists studying cures for cancer who make a decent salary, but I saw, look, I don't know how true this is, but I saw on SixBuzz on my phone,
Yeah.
there was some woman who was apparently getting paid $2 million a day to let people watch her sleep. I don't really know how. I don't know if that's really true. But if it is true, then it's weird to me that the markets or whatever, however you want to,
Because we're dumb monkeys.
Even if you said $1,000 a day,
right? It's
that's ridiculous. We
So I think to me
we
that's-
live in a funny place, my friend.
that's clear evidence that maybe we don't live in what people call a meritocracy. The idea being the harder you work, the further you'll go.
Most
Right.
definitely not the case.
Not anymore.
But that's not even the law of nature. Like, no animal gets to have that pleasure.
Yeah. So yeah. Anyway, I think some serious changes have to happen in society
Right.
in order for us, because right now we have countries that have nuclear weapons and we need scientists.
Right.
And in particular, of course, I'm biased because of what I studied, but
Right.
but one of the reasons why I study what I study is to learn something about space and time, and in particular to maybe learn if we can go beyond Einstein's speed limit, because in Einstein's theory you can't go faster than the speed of light,
Right.
which means that it takes a very long time for us
To get anywhere.
to get anywhere in the universe.
Right.
And we've all seen like Star Wars and Star Trek. I don't view these things as science fiction. I want, of course they are science fiction, but I want to be able to have humans traverse the cosmos.
Right.
Right.
And
If
in order
it's
to do that,
conceivable, it's
and in
possible.
order to do that, we need to figure out something, to go beyond Einstein, to figure out something
Right.
about space and time.
Right.
So I think science should be more funded.
That
For sure. Yeah.
That's exciting. That's crazy. I had a very good question lined up, but I've lost it. It'll come back to me.
We can do string theory. You can do what I work on is something called, this might pique your interest, holography. The idea that the universe is, the poetic way to say it is the idea that the universe is a hologram.
Oh. Okay.
We could do that. We could
Hold
do
on.
that. Yeah.
Okay.
That reminded me of my question. It's a good question. 'Cause
Right.
I think you'll have, I don't know, maybe strong opinions on it. So you're talking about the funding of researchers and scientists and how it's, really terribly underfunded. But the same can be said. There's a lot of money in the private sector and in the corporate sphere.
Yeah.
And you do see a lot of researchers and scientists sell their soul proverbially to these corporations
Yeah.
and are fabricating science that is being used to, hurt people.
Right.
And I think a lot of people kind of have a problem trusting scientists,
Yeah.
especially at the theory phase of their research. You know what I mean?
Yeah. I think that's one of the reasons why theory-based sciences are so underfunded, is because you're right. Like, people want to see within our society, our capitalistic framework, and there are elements of capitalism that I really love. There are elements of capitalism that I don't really
Yeah,
love.
same.
Right? I think it's produced. Look at this place. Like, it's produced a lot of great things. But in this framework, people want to see results, and they want to see what technology you're making to help us make products in order to, create companies to sell these products, right? And so people studying theory-based sciences are viewed as, well, it's theory. What application does it have? Mm-hmm. To which I will counter. So I just described to you the whole saga of quantum field theory and quantum mechanics. In the early 1900s, there's so in the 1800s. So I mentioned quantum electrodynamics. Well, for every quantum theory, there's a classical theory of that. So there's classical electrodynamics, which is some guy called Maxwell in the 1800s discovered the equations for this. Mm-hmm. So if you take classical electrodynamics and you try to ask, when you heat something up and it glows, right? That's light. Mm-hmm. What is the energy associated with that light? And when you try to apply classical electrodynamics to the question of what is the energy of that glowing thing, you get infinity, and that doesn't make sense, right? Because if it was infinity, it'd be destroyed.
Right.
So that seems what question is that? That seems such like a mundane question, right? Who cares? Well, this guy called Planck in the early 19th century said, that's weird, let me try to solve this. And in solving it, the answer to the solution is quantum physics, right? Instead of light sort of being a continuous wave sort of thing, light was a particle in quantum physics. And so if you put that into the equations, you end up getting a nice, they call it a Planck distribution.
Do you know how I would have started that paper? But wait. There's more. There's more.
Exactly. That's what this was an idea. This is a theory. This is all mathematics, right? Mm-hmm. All theory. Mm-hmm. Okay, you ask the question, you get infinity, you come up with the theory, quantum mechanics. Quantum mechanics underlies everything in our society today. So without asking the question, this stupid question, let's say, of, well, this glowing object, you get infinity when you try to apply it. Without asking that question, we wouldn't have lights, we wouldn't have these microphones, we wouldn't have GPS systems, we wouldn't have anything. So the idea that theory-based science doesn't produce things that we can use is ridiculous, because GPS systems don't work without Einstein's theory of relativity. Phones don't work without semiconductors, which quantum physics underlies, right? So we need theory-based sciences because we don't know what we're going to discover. That's the whole fun of it. That's the whole beauty of it, right? We may discover something in quantum gravity about the structure of space-time that will allow us to traverse many millions of light years in a second. We don't know. So that's why that's my argument for the funding of theoretical sciences.
That's a very good argument. I think that's a good spot to wrap it up for the time being. We are definitely getting you back.
Okay, yeah, for sure. I'd love to.
A lot more that we want to cover.
Yeah.
We are going to bring you back.
Yeah. We didn't even get to
freaking thrill, man. Honestly, thanks for coming on.
Thank you. It was a pleasure.
This was like.
No, it was incredible. Yeah, that's definitely gonna bring you back. Definitely gotta go.
Yeah.
It really did.
It does. Yeah.
Definitely gotta go deep into some topics. That's for sure.
Yeah, I'd love to be back. Yeah.
I'm gonna sit down and listen to this episode 4 or 5 times and just make notes. And just be
it's a good introduction. It's a good introduction.
Exactly.
It was very, very well done. Very well done.
Thanks for having me.
Thank you, sir,
for joining us. So this has been Think on That. This is the Everything and Anything podcast. We post our episodes every Monday except for the last 2 weeks. Sorry about that. 6 a.m. Eastern Standard Time. Like, subscribe, follow us, and check out our social media platforms to see Mike here and follow his story, because we'll be bringing it back anyway. So
yeah.
But thanks for joining us.